Good afternoon, everyone. Today's session for the sharpen saw is about joint modeling in FEA. And this will be the start of a series. I'm calling it part one of unknown because I don't currently know how many we will present. There's a couple of additional topics that we may need to cover, and also it depends on the feedback that we get in terms of which sessions and how many of them we'll present. So in this first part, I will cover a little bit of some examples of joints, but what I'll spend time on first is how to model and what the differences in modeling parts and assemblies. Then a bit about what's this fuss about joint modeling, why do we care, some common joint types, and then the case for simple joint modeling. So we look at all of the common joint types then and what the complications are, and then why we want to try and simplify it. So if you go to part modeling, typically it can be anything simple. It can be a bit more complex as well. To model it correctly, we need a CAD model. We need a material property for this, loads, constraints, and then we're pretty much ready to run. So apart from this, we measure the part, apply all of these, and we can run. In this case, something like failure would typically be some kind of a stress limit that we specify, whether it's plasticity or fracture. It can be displacements, but on a part level, we tend to have relatively simple failure criteria. Whether the part is simple or a more complex part or even highly complex, as long as it's a single part, it's relatively simple to do. Once we get to assemblies, it becomes a lot more difficult. So if I look at the Eiffel Tower as an example, there's a lot of beams in there, and each of them is joined to other beams and other sections. And that sections, how they model together or join together, actually play a significant role in how the structure behaves. So apart from just being more difficult, it's a lot more time consuming because every one of these beam sections become kind of like a part, and then we have to specify how they join together. Now, if we need to accurately model an assembly, we again need geometry similar to a part. We need loads, materials, constraints, but we also need to know how the parts are joined together. So that part joining together is pretty important here because we also need a way to model how it will fail, and that means we need to know what information to extract to determine whether or not it will fail. So an assembly is typically a statically indeterminate structure. A part can be as well, but most assemblies will be. And if a structure is statically indeterminate, it means we need to know the stiffness of the structure in addition to where loads are applied and where constraints are applied. So if that stiffness is wrong, we get the wrong load distribution, the wrong load paths. In other words, we get the wrong reaction forces. So to get an assembly right, I have to have the stiffness distribution correct, and that includes the stiffness caused by the jointed connections. So that's why we need to model the joints, the stiffness at least correctly. And then from there, we need to extract some results to be able to determine whether or not the joint will fail. If we actually go to the level of let's model everything in detail, we'll end up with some kind of a model that's pretty much impossible. So if we model every bolt, nut, washer, weld, rivet, whatever, in a lot of detail, it's simply not possible. So we need some kind of a simple representation. As far as I'm aware, the Eiffel Tower has got over 1 million rivets. If I model each of those using 1,000 elements, that would require 1 billion elements to model. And that's just the joints or the rivets. That's nothing else yet. Okay, so when we do the simple representation, we need it to be accurate. Accurate in terms of, again, stiffness is the most important for the joints, because as long as that's correct, if the rest of my structure, each component in the structure is reasonably represented, the load transfer will be correct for each, meaning the stress distribution for each of those should be pretty good. So if I look at the common joint types, we get bolts, obviously, rivets, seam whorls, spot whorls, glue joints, and so on. So glue joints is something I don't see a lot, but I think it's actually a pretty good joint and useful joint to have. Obviously, lots of complications as well. In the next sections, we'll spend a bit of time on bolts and rivets, touch a bit on seam whorls. I'll mention something on spot weld. I don't specifically have a slide on that. I'm not going to cover glue joints in this as well. Okay, so let's look at the bolted joint. Let's say I want to model this in extreme detail. So I've got two plates. I'm going to model everything in solids, and I want to determine whether or not that bolt will fail due to whatever loads I'm applying. To correctly model that, what I need would be firstly contact between the bolt head and the first plate. If there's a washer, contact between the nut and the washer and the plate, between the plates, possibly sideways, depending on whether I want to model that gap and how large that gap should be. Contact then from the shank to the bolts, but also in theory, contact between the nut and the threads. So or the threads on the shank of the bolt. So all of this, bolt head, nuts and washers and plates, all of those just for the contact. We also need to model friction correctly, because as I tighten the bolt, what keeps the bolt in place is the friction. Without the friction, the bolt will simply loosen over time. But also, a lot of the loads will be applied in friction. So in other words, let's say I preload this. If I load this one to the right, and I constrain the left-hand side, most of that load will be transferred from there to there through that interface there, which is in friction where it transfers the load. So I need that correctly. I must have the plate elements modeled in solid if I want to model using the preload, because what makes the preload work is a through thickness stress. And the only element that has through thickness stress is a fully solid element. So if I need to model this, it becomes a pretty expensive simulation. I cannot use shells for this if I need a preload, at least if I need a preload in the simulation. So we then need to apply the preload. We would need plasticity curves for the plates and the bolt if needed. The plates maybe, but the bolt definitely. Again, if I want to model this in detail, including the threads. So the problem with modeling this is the results will probably be useless, because what I'll have is I'll have to tighten this nut, which will be a really expensive simulation. But one of the things that comes out is, due to the stress concentration in the threads, we'll end up with plastic deformation in the threads. The moment plastic deformation occurs, it's a lot more complex to try and determine when it will fail, whether it will fail, and how it will fail. But also, we have a pretty nasty requirement in a lot of some codes, SANS codes, Euro codes, British codes, all of those. Often they'll have a requirement that says for this kind of a structure, you're not allowed any plastic deformation when you load it using X load. In this case, because of that sharp corner we have and the amount of torsion we apply there, we will plastically deform the nut in and the bolt in those roots of the thread. So effectively, we've broken this rule. That's if you really want to model in that level of detail. On the other hand, there's a lot of scientific evidence that can tell you how strong a bolt actually is, what the strength in the different directions are, and so on. So that's why we prefer to actually not model in that level of detail, because I would then have to have all of those failure methods and so on exactly the same as you would need to test. I'll have to represent in the finite element model. So there's measured data, in other words, and it's different theories and methods that's calibrated to explain the difference in strength due to tensile and shear loading, combined loading, but there's also information related to the fatigue behavior. So that means if I've got the forces on the bolt, I don't care about what happens in the thread. I have enough information if I use some or one of these theories and methods to calculate whether the bolt will fail and whether there's going to be slip between the different parts. So what we need is, instead of a fully detailed model, a model that accurately calculates what the forces in the bolt will be, and then possibly that shear force, depending on, again, different ways of modeling. Now, we'll see, I'll dig a little bit deeper towards the end, specifically into bolts. So hopefully that will explain it a little bit better. Okay, if we go to rivets, again, let's start with, we want to model it in detail, which again is obviously a bad idea. But we start with the rivets, we get two types. The one that's a single part that's forged almost on the other side into shape, and these kinds of rivets where there's two parts and the one deforms the other and so on. So there are lots more interesting shapes and sizes of rivets. But to model this accurately, we need, again, contact modeling. And again, on the same level as for the bolt, I'm just not going to explain all of those contact pairs and so on again. We again need friction properties. We need plasticity curves in this case for at least the material or the materials of the rivet itself. Because if that one goes through and then you shape it on the other side by plastically deforming it. For this kind of a rivet, you pull this through and that deforms that shank section and it bulges out. So to do that accurately, we need the plasticity curves to be able to do that forming. We'll again need solid plates, solid elements for the plates. Otherwise, again, the through thickness stress is wrong, meaning my connection will not work well. So that preload that we'll get will be badly represented. We also need to model the rivet process to get to the right final shape. And in the end, we'll end up with an analysis with large strain, remeshing, sliding contact, blah, blah, blah. And we'll end up with insane run times. And that's just to get it into place. Okay, so similar to bolts, there's methods that exist based on measured data and lots of tests to determine the strength of every rivet type, direction, load combination, and so on. So if we can again get the forces, I don't need to model this in a lot of detail. I can model this in a lot simpler way, extract the forces, and then use it in a separate calculation to determine whether or not it will fail. So we need, again, a method to accurately get those forces. And if I just look at some examples, some viable methods, we can have rigid connectors. So if I look at that plate, I can have, let's say, a node on the top plate and the node on the bottom plate rigidly connected, and I can extract that forces. I'm not saying this is the best method, it's just a viable method that for some combinations of plate thickness and stuff can actually give decent answers. But we can also go into a bit more detail, some kind of a beam connector between them. So again, connect from there to the other plate, but now with a beam element between them. And for that, we can tweak the cross-sectional properties and elastic model and stuff to more accurately represent the stiffness of that rivet as needed. And again, that can go to a single node on this side and a single node there, or if I've got a hole there, I can, in some way, the rigid connection or otherwise, connect that center for the beam element to that surrounding area. So then you just spread the load a little bit. And we can also use a spring element. So if you're used to Nastran, the MSC Nastran bush element, we can specify a spring stiffness in each of the 6 directions. So it may be an easier way to calibrate instead of using beam connectors. What we want out of any of these methods will be the force, shear forces, bending moments, axial forces, whatever, and that we plug into, again, the method that's used to represent the actual failure criteria for the bolt, or the rivet rather. If you look at seam welds, it gets a bit uglier. So if I look at the details of a weld, if I want to model what's happening there, we end up with lots of interesting stuff. We need to model thermal and structural simultaneously. So the structural to say where the material currently is and how it deforms, thermal, how the heat distributes. We may even, in extreme cases, want to model the electrical part to model where the heat is coming from, although there are simplified methods that can do that. We need plasticity curves over an insane range, anything from room temperature up to almost the yield, almost the melting point of the material. So that would mean it's a lot of tests that you need to do before you can get that information out. There's phase transformations taking place, We need data for the weld material and the parent material, which are often not the same. I make note there of the weld material. Some of the weld processes does not have a weld material. So it simply melts the parent material, two parts together directly. Okay, we also need to model the CAD data correctly. In other words, what the shape of the weld is, how it progresses, and so on. We can also have additional information in terms of the thermal boundary condition, how quickly it cools down. It ends up being an insane simulation, which is extremely useful for predicting distortion due to the weld process, which is something that is a definite problem with welds, which the more you can solve before you actually try to weld the first one, the better. But unfortunately, it's useless to determine the strength of the welded joint. As it's as simple as if you look at the stresses in the weld at the end of that process, it's pretty close to the yield strength of the material. So just the residual stress is already extremely high. And you have very little control over that other than slight changes to the process. Okay, so instead, for welded joints, we typically use a code that's based on measured data of different types of welds. Some examples, Hero Code 3, BS7608, and so on, as methods that says we define, for example, a fatigue curve, one example, for a specific joint type. And that fatigue curve already includes the geometry and all the defects and stuff that's caused by the weld. So effectively, heat affected zones, the change in properties, everything, including the stress concentration at the root of the weld. So what we need to model for that is the stress that would have been there if there wasn't a stress concentration. So that means we on purpose do not we model the effect of the weld or a very simplified weld to extract that kind of information. Yes, there are methods that you actually model with a specific geometry, very small radii and stuff, but that tend to work well on lab kind of a scale test. It doesn't work typically on massive scale. So using this kind of a method again, we do not model the weld itself, and we definitely do not model the weld process. All that we need again is information about the stress state and some kind of a code that specializes in exactly that. We can then extract the life or the strength of a specific joint. Now, spot welds, there was an image earlier on. That also has very similar kind of issues to this. It's just we don't necessarily have a parent material there. It's just the material that's welded together, but we still have nasty stress concentrations and so on. So again, instead of trying to model that in detail, we'll rather use a simplified method and then an external calculation to determine the forces and the strength of the weld. Now let's look at some examples of how we can model a bolted connection. So let's say I want to model this first in the most detail possible, except I really don't want to model the threads at least. So what I can do is I model everything with solids. So I specify contact between all of them. And then in some way, there's lots of ways to do it. I can specify preload on that. And now the structure is preloaded. After that, I can now apply my loads. Now, just a couple of things to take note of. Let's say I clamp the bottom one on the left-hand side and I apply load on the top plate towards the right. The load is transferred in shear on that face, but also because that force is in the center, there's a bit of a moment about that face, meaning I need to counteract that moment. Now, the way that it actually is transferred is in compressive stress distribution over that face. So if the stress on this side is, argument's sake, higher than on this side, I've got a bending moment towards the left. So that bending moment is not directly transferred to the bolt itself. The purpose of the bolt is keeping these plates together and they slide on that face effectively. So even if you hand tighten it, what will happen is due to that load, it will slide and will press there on the one side of the bolt and there on the other side of the bolt. So it's a very short section that's actually in shear. The rest has a very small amount of shear, at least in the bolt. Actual load depends critically on the bolt dimensions, the plate dimensions, the preload, and the load applied. If I try to pry this apart, if my bolt preload was argument's sake 1 kilonewton, and then I apply 100 Newton there, the load of the bolt does not go up to 1.1 kilonewton. What happens is, as I try to open it up, the pressure on that face decreases slightly, which effectively, that pressure initially is what caused the bolt preload. So because of that, the total load on the bolt actually goes up by a smaller amount. So the exact amount and the ratio depends critically on the thickness of the plate and the dimensions of the bolt itself. Okay, so if I model this in detail, I'll get that nice pressure distribution using solid elements. So this is a great way to model the kind of joints where I'm interested in the size and pressure distribution. So if you need to avoid leakage, for example, so this is a face that's supposed to be squashed together with a pretty high stress, because I don't want water leaking out or air leaking out or something. This is a great way to model that. It's not such a great way to determine whether or not the bolt will fail, because again, looking at the stresses on the bolt is a very crude representation of what actually happens in the bolt. So what we'll need is extract from the solid model now the forces, possibly moments and so on, and then use an external calculation to determine whether or not it will fail. So one level down, or a slightly simpler way of modeling, would be we still take solid elements for the plates because I'm interested in preload still. But then instead of the shank using solid elements, I use a beam element that runs through it. And then I have to in some way connect those end nodes to an equivalent of either the washer or the nut or the bolt or something. So there's lots of ways to do that, and that's some of the things we can look at in future session. Just some examples would be, I can rigidly connect that one argument's sake to that whole face. Not a great idea, but it's viable. I can also connect it just to that inner edge, which is probably slightly worse, but I can also model a washer in there and connect it to the back side of the washer. So then at least I have contact there instead of rigidly connecting the node of the bolt to all of these. So the bolt can slide if needed, it can separate if needed, and so on, which is something that the rigid can't do. The main advantage of this method, though, is we immediately get forces out of the bolt element because, well, we have an element that mainly works in forces. If I have solid elements, I have to count the force for every one of those, or I have to integrate the stress to find the shear forces. Okay, so the next level down would be if I replace the shells, or the plates rather, with shell elements. So I have a mid-surface and a mid-surface. At that stage, it's firstly impossible to model a preload correctly. A preload can only be done correctly if I've got the stress through the thickness, that compressive stress, and for that I need a compressive strain. Otherwise, the stress will be calculated wrong. Shell element does not have a strain through the thickness due to a load applied in that direction, meaning no stress either in the thickness direction. So you will utterly get wrong answers and weird distributions. If this was a solid preloaded, I'll see that whole face being in contact with a pretty decent load distribution. If this was a beam element, a shell, I'll probably see they're close to the bolt, they're heavily in contact and nothing else touches, or a very, very low. So that distribution will be, as I say, utterly wrong. So that's it. The next one is, you then typically use a beam element or a rigid, even if you really want to go that far, to connect the mid-surface of that one to the mid-surface of this one. And again, we have the choice of connecting directly to a node on the surface, or rather to an area which represents the area where the bolt is. And node-to-node connection is usable for certain kinds of structure. In general, it's preferred to rather distribute the load over a larger area. Otherwise, you end up with a pretty insane stress concentration that doesn't really exist. Now, the moment you do that, I've got a mid-surface and a mid-surface, a beam between them, and I don't care too much how they're connected. The beam is in some way connected to the mid-surfaces. If I again constrain this plate, and I apply a load to the right, what will now happen is the shear force is transferred from the top plate to the bottom purely through the beam, so not in friction at that location. And in addition, it will bend because there's a shear load where, let's say we can find that point and load that to the right, that beam element will bend towards the right as well. In reality, neither of those exist on a beam element because even if it's hand tightened, it will transfer that shear over that very small area, and the bending moment will not be applied through the bolt, or a very small portion of it goes through the bolt. The rest simply goes change in pressure distribution. So that's some of the things you just have to be aware of. So if I have shell elements with a beam and I have contact between them, which is a lot more expensive than not having contact, obviously, then at least that bending moment due to this part and that part being in contact in that direction, that distribution can at least counteract that bending moment. Okay, so I've mentioned there that the length of the bolt is wrong because in the length direction it should be that, not from the midplane to the midplane. But in the shear direction, the bolt actually doesn't really have a length because it's purely over that area that the load should be redistributed. Okay, so that's just a couple of examples that I tried to go through just to explain what the complications are and touch on some of the modeling techniques. If you're interested in more on specific types of joints, please let us know and we'll add some sessions on specific types of joints, different ways of modeling, and examples of analytical methods to calculate the strength. So in conclusion, if I look at joint modeling, it's important to model joints. It's important to model them reasonably correctly in terms of stiffness. We seldom have the freedom to model a joint in a lot of detail, so we'll tend to simplify as much as possible. But we need a method to get all the info we need to be able to extract and calculate after the fact whether the bolt or a rivet or a weld will fail. But it also needs to be accurate. So if that is not accurate, my load distribution will be wrong, or load paths will be wrong. So I'll effectively get bad answers out of the simulation. So it's important to understand the different modeling approaches when we model some kind of a joint. So this last one was a simple example where we can model a a bolted connection using solids, combination of solids and beams, shells and beams, shells and ridges, and each of them has its advantages, disadvantages, and complications. Okay, so that's what I wanted to discuss for the session.
Thank you for that. That was great. You lost me a little bit when you were talking about the preloading of the bolt, and then so if you preload the bolt with 1 kilonewton and you load it with 100 kilonewtons, it's actually a little bit less. Why is that? Could you just repeat that, please?
Okay, so for that, and I apologize beforehand, it's not going to be a pretty picture, so let's try and model something. Okay, so let's say that's where my bolted joint will be, my head, my nut, and then the two plates that we end up with. Okay, hopefully it makes sense. If I look at this joint connection, what I've got is a force applied to the head vertically up through the plate, and it's got a stiffness of its own. So if I look at that connection, this effectively is a spring stiffness, and that is a spring stiffness. Okay, so sorry, that last one is really badly done. So compressing that plate, I'm acting against that stiffness that represents the stiffness of the plate. So effectively the thickness, the elastic moduli, and the area over which I apply that. So that all of that I can simplify as a single spring element. And the bolt on its own also acts as a spring element. So that's effectively one that's in parallel. And on that side, they're in the same location in space because the bolt is welded bolt. So I can connect them together. But on this side, there's a little bit of, let's try and do it slightly neater. There's a bit of a gap initially. So think of this nut being, as it's tightened, it's open, I move it closer and closer. And at some point, it's just touching. If I want to preload the bolt in tension, I have to apply some kind of a force down and up on that region. So that represents my preload in the bolt itself. So that's distance there is effectively how many times I tighten it and how times your pitch of the thread. So that's the amount of material I'm effectively removing from that section by tightening this. So what I'll then end up with is if I pull them together and then lock them in place, there's a tensile load going through this and a compressive load going through that. And the total load of those are the same. Does that still make sense?
Yes, that makes sense.
Okay, now the problem is what happens if I now apply load that's not enough to separate on that face as yet. So as I apply that load, this one, which happens to be in compression initially, it's unloaded,
Yes.
and this one is loaded. So the compressive load decreases, the tensile load increases, but the actual change in load, because this is my bolt, the actual change in load depends on the ratio of the stiffness between these two. So let's take an example. Let's just use stupid numbers. So this will be 1 Newton per meter and 1 Newton per meter, or rather 1 Newton per millimeter, 1 Newton per millimeter. And it's currently set up that there's 10 newtons going through this one in compression and 10 through that one in tension. If I load that one with 1 Newton, then the sum of those two have to be, because it's a negative compression, positive tensile, the sum of those is 0 initially. But now this one goes from compression 1 Newton to compression, so let's just put numbers. So there's 10 and 10, and I apply 1. So that drops from 10 compression to 9.5 in compression. That goes from 10 in tension to 10.5 in tension. If I look at the sum of those, it perfectly balances the load that I've got. But that load effectively doesn't directly go through this. It's simply because that is unloaded. So that preload there, the compressive preload there is carried by the bolt. But that compressive preload is reduced, which means the bolt doesn't work as hard. Now, typically, this one is a lot stiffer than that. So you tend to have a lot lower ratio. So this, instead of 1 Newton actually changing it by half, it'll probably rather be something like 1 Newton only changing it by 0.3 Newtons or something, maybe even less.
Okay, that makes sense.
Yeah.
All right, thank you.
Pleasure. Anyone else? Okay, so there's no further questions. That concludes our session for the day then. Please let us know if there's specific joint types you'd like more information and how to model them and how to calculate whether or not they will fail.